In this video, we're going to predict products of a chemical reaction. In this first example, we have calcium and oxygen. Well, calcium we know is a metal, and it's a metal in group 2. It's an alkaline earth metal. So calcium wants to form a positive 2 charge. Oxygen is in group 16. It wants to form a negative 2 charge. And we know that metals, when they encounter nonmetals, form ionic compounds. So we know it's going to be charged. So I would predict that calcium is going to form a +2 charge. Oxygen is going to form a negative 2 charge. So they'll want to come together in a 1-to-1 ratio. Okay. So I consider the charge when I come up with my Joseph-Proust definite proportion. So now I've just got to balance. I've got 2 oxygen here. I've only got 1 here, so I need to put a 2 here. And I need to counterbalance the calcium with a 2 here. So where I've got 2 different types of material coming together to form one type of material, this is called a synthesis reaction. Because I'm synthesizing something, I'm making something. Let's consider this equation here. I have ethene, which is a gas similar to natural gas. So I have a gas and oxygen. Now, this essentially, I recognize this as a type of fuel. So we know that fuels burn. You can tell it's a fuel because it just contains carbon and hydrogen. So typically that would be a fuel. So fuels, when they encounter oxygen, burn. And that essentially means we add oxygen to each type of element. So we add oxygen to carbon and we make CO2. We add oxygen to hydrogen and we make H2O. So this is just something that you'd have to accept at this stage. Whenever you add oxygen to a chemical that's a fuel that contains only carbon and hydrogen, think of it, you add oxygen to carbon and you always make CO2. You add oxygen to hydrogen, you always make H2O. So now we can go ahead and balance. So we have 2 carbon on the left, so I'd have to put a coefficient 2 over here. I have 2 hydrogen on the right, but I've got 4 on the left, so I'd have to put a 2 here. So now I have 4 hydrogen on both sides. So finally my oxygen, this 2 multiplies that 2, so I have 4 oxygen over here. Plus I have 2 oxygen here, so I have 6 oxygen total. So I'd have to put a coefficient 3 here, so I now have 6 oxygen on the left side also. Whenever you add oxygen to a fuel, you would call this combustion. Combustion is a chemical word for burn. So whenever you burn something, you're combusting it. Notice combustion is not the same as synthesis, although they both involved oxygen. Here I was making one thing from more things. Here I'm not, I'm just making different things. So it's slightly different. Here in our final example we have 2 ionic compounds. So when you have 2 ionic compounds, there's a chance that you could form a net product. You could have a net ionic equation. So something's on the right mustn't be aqueous. So the template that we're going to suspect is AB plus CD. This should give AD plus CB. So if you imagine the cation of one compound goes with the anion of the other ionic compound and vice versa. So ADCB. So in this case, we have A is K plus. B is Cl minus. C is lead 2 plus. And D is NO3 minus. Now notice at this stage, I know that there's a factor 2 here, so really there's 2 NO3 minuses, but I only want to know what one of them is. I'm interested in what's the identity of one of you. I can always scale you later. So I know that K plus goes with NO3 minus, so K plus goes with NO3 minus. And I know that the sum of charges must be 0. So right now that will give me 0, so I can write that in. So K NO3. And I could look up in a solubility chart that that's going to be aqueous. So right now that's not a true product because it's aqueous on the right and left. So there's going to be no net ionic equation. So it's product for balance in mass terms, but that's all. It's not a true product. C, I know, is lead 2 plus. And B is Cl minus. Well, I know that 2 plus and a negative don't sum to 0, so I know I'm going to have to scale the Cl by a factor of 2. Now, when you write this as a chemical equation, that coefficient is going to have to be part of the material itself, so it's going to be a subscript. So this is going to be PbCl2. Okay, so this multiple here becomes a subscript to represent it's part of the unique chemical itself. I can look up in a solubility chart, this would be a solid. So I know that I can't split solids up, so I have a net product. This is my only true product. Now I can proceed to balance the equation. I have 1 potassium on both sides, so that's good. I have a lead on both sides, that's good. I have 1 nitrate on the right, but I have 2 on the left, so I'd have to scale this entire chemical by 2. So I have 2 nitrates now on both sides. So I've now got to go back and scale that chemical because I needed 2 potassium on both sides. But conveniently, that number 2 scales the chloride to match the chloride over here. So now it's balanced. This unique template down here, this AB plus CD, this is a double displacement or double replacement reaction. So I'm not only balancing, I'm predicting products and I'm identifying type of reaction, double displacement versus combustion versus synthesis. There are more types of reaction. But this is the idea behind identifying what type of reaction. Once you've identified the type, it can aid you in predicting what the products are.